Alright, I'm going to make an attempt here to explain a pressure enthalpy diagram. If you read a basic HVAC book, you're probably not going to really be exposed to too many of these pressure enthalpy diagrams. This is something that probably taught more in engineering school. Kind of more the technical side of refrigerants and refrigeration. If you just understand some of the basics that's described in an HVAC book, that's going to get you pretty far in terms of doing some DIY refrigeration type shit. So I first got exposed to these by reading some technical refrigeration books from the 1920s, 1930s. These things are pretty valuable. This here, this one's an R290 pressure enthalpy diagram. Excuse me, it's a log pressure enthalpy diagram. So it's log pH diagram, H being the enthalpy. Any diagram for or any refrigerant is going to have a diagram that looks something similar to this, where we have this big saturation curve here, and the general relationships are going to remain largely the same. It's just the shape and the values are going to change. So this one here is for a this is for R290, and it's metric. It's in the SI system. I have one for the Imperial system that's listed in BTU per pound and PSI instead of bar, and so on and so forth. It looks exactly the same. All the relationships are the same. The general curves are all the same. It's just the units are different. But those are a little harder to come by. The one I have is in the ASHRAE book, and it's a little lower resolution than this. So we're just going to use this. So I'm going to ramble on for a while. This is going to take a while, but I find these diagrams to be very useful in trying to better understand some of the principles involved in refrigeration. And once you get a handle of this, if you're like me, then you'll start to think about your refrigeration circuit on these diagrams, because you can actually draw out the circuit on here and infer a lot of useful information about it without even really being all that concerned about the actual values and the quantities involved, other than actually charting it on here. The general shapes and the trends really help you get a hold of refrigeration. So this diagram displays a lot of information. Like I said, pressure on the one side, enthalpy on the bottom. We have temperature, which is very important, specific volume, these green lines, and then entropy. I'm not going to get into entropy as much if I get through this video at all. The heat content, the enthalpy, listed here at the bottom. If we travel from left to right, we're increasing in the heat content of the refrigerant. We go from the bottom to the top, we're increasing in pressure. This is logarithmically. Largely, I think, because it fits on the page a lot better, it's easier to work with, and it more or less linearizes the temperatures. We go upward on this side, we see higher temperatures, and we mostly left to right on this side, we see higher temperatures. In the middle of the horn, temperatures are horizontal, as this is the saturation curve. So anywhere within this curve, the refrigerant exists in a both a vapor and a liquid state. So where can we start? Well, for instance, let's take a tank of propane. Here's a tank of propane right here. It's not quite full, and for the sake of the argument, we're going to call this BTU per pound at the bottom, not kilojoules per kilogram. Just it's a little better for my thinking. Okay, I have to usually convert in order to use one of these charts that are in the SI system, because I don't work in the SI system much. I should, but I don't. So, as I said, this here at the bottom lists, and again, we're going to say BTU per pound. The BTU content per pound of refrigerant, whether it's in a liquid state, a vapor state, or both. Okay, so looking at this tank of refrigerant, let's assume there's a pound in there, because whenever they're new, they have a pound approximately. That propane exists in there, and let's say the tank's about 80% full. We know it's not going to be any more than 80% full, because that's kind of the danger limit. It exists in there in both the liquid and the vapor state. I can shake it around, I can feel the liquid inside. But inside this tank, it's got a relatively high pressure. Let's say the temperature outside is about 60 degrees right now. And let's assume the tank is about the same temperature, which is about, sorry, let me look again, about 95 pounds per square inch in that tank. So it's not super high pressure, but it'll come out of there booking pretty good. It'll squirt you. It'll be cold. So that exists in there in the liquid and the vapor state. And at the surface of the liquid, you have molecules of propane that are jumping into the vapor state, and molecules of vapor that are jumping into the liquid state. And if everything's at equilibrium, the temperature is not changing, and the pressure stays constant, essentially the same amount of molecules that are jumping from liquid to vapor and vapor to liquid are equal, and they cancel each other out. In which case, we maintain a certain the same quantity of liquid and vapor. Now, let's assume that the whole thing is at equilibrium with the room here, and it's about, we're going to say it's about 60 degrees Fahrenheit. We're going to go with about 20 C on this one. We're just going to point right here. Okay. Now, the liquid exists over here on the saturated liquid line. Okay. If we add any heat at all, we add any enthalpy, we increase the enthalpy of the liquid, we're going to end up vaporizing some of it. Likewise, the vapor it exists over on the other side at the same temperature on the vapor, the saturated vapor line. And if we remove any heat, it's going to begin to condense. All this is going to occur. All this is existing at the same pressure right now. Now, let me point out some of these temperature lines here. Right here is 40 degrees C, and there's 40 degrees C. They're directly across from one another because there is a direct relationship between the temperature and the pressure whenever you are at or near saturation. Okay. Over here in the vapor state, if we were talking purely vapor, we could increase the temperature of a vapor, and we're going to cross these what are called isothermal lines, lines of constant temperature. And if we increase in pressure, we're going to cross some of those isothermals, and we're going to increase in temperature. We know that from common experience, and if we understand the basic gas laws, which apply to perfect gases, but this is not a perfect gas, but the law still applies. So if we increase the pressure, we're going to increase the temperature of the gas. Over here on the left side, in the pure subcooled liquid area, if we increase the pressure, now although these lines aren't drawn on here, they're more or less vertical. So if we increase the pressure, the effect on temperature is not great. It does exist, but it's not substantial by any means at all. And back to the tank of refrigerant itself, the propane. If we have that liquid sitting here on the saturated liquid side and the vapor on the saturated vapor side, and we start to add heat, that is, we increase the temperature of the tank slightly. Let's say the temperature in the shop here increases, so the tank temperature increases. The amount of average kinetic energy in the liquid starts to increase, so more molecules of liquid start to enter the vapor state, then vapor enters the liquid state. So we get an overall trend of increasing in enthalpy for the entire system, the entire pound of propane. So we get some molecules that start to, we get more liquid turning into a vapor. So we get a general trend across. We're increasing in enthalpy for that amount of propane that goes into the vapor state. Eventually, if the temperature in the shop continues or stops rising and the tank comes to equilibrium, it's going to come to an equilibrium at a slightly higher temperature than it was before, and the overall enthalpy of the entire system is going to remain a little bit higher. And then the opposite is true. If we lower the temperature in the shop and it gets down to 50 degrees in here, we're going to get more condensation. We're going to start to travel in this direction. So this can be really useful for looking at a refrigerant system, because if we're not just looking at a simple tank, for instance, if we were to just vent some of this propane off and lower the pressure, we know from common experience and from reading our refrigeration texts that the temperature is going to drop. And we can imagine what would happen here on this diagram. So here's the same diagram, and this is one I've actually used a little bit. Every once in a while I fool around with these and take various pressures and temperatures throughout the system and chart them on here to see what they look like. So this black line here, ignore the green ones for the moment, and also ignore this extension over here. We're just going to talk about this little four-sided figure right here, okay, with the horn on the end. We can describe our basic vapor compression cycle with this black line, and the different states that the propane exists in throughout this cycle. So, for instance, we know that there are cases where all the refrigerant, that is in a vapor state, and that exists within the suction line coming back to the compressor, in the compressor itself, and then the discharge from the compressor whenever the gas is superheated, and it's not condensed at all, it's just all superheated gas. States where we know places where we know the refrigerant is liquid, or at least partial liquid, is in the condenser and in the evaporator. The metering device is an interesting place because we can have both a liquid and a gas existing in there, depending on what kind of metering device we're talking about and what part of the throttling that we're discussing. So we have 4 major lines comprising this shape, and we have 4 major components in a vapor compression cycle. We have the compressor, we have the condenser, we have the throttling or the metering device, and we have the evaporator down at the bottom. So if we look at the isothermals and where the isothermals exist, and we look at the general trends of the pressure on the left side, it's cut off in this one, but we understand that as we go upward, we increase in pressure, and as we go across, we increase in enthalpy, in the heat content of the refrigerant. So pointing out that this is the compressor right here, right before the compressor we have a saturated vapor, and then by the time it actually reaches the compressor, it's increased in temperature slightly, and it's a superheated gas existing at the suction pressure, this lower pressure here. As it leaves the saturated vapor line and enters through the suction line, and picks up some extra heat, and the vapor starts to become more rarefied and increases in temperature. We can see that on the chart because we're crossing some of these isothermal lines. These are lines of constant temperature. So the temperature here is 80 degrees C, the temperature here is 80 degrees C. But what changes across that isothermal there is the pressure. It changes the specific volume, it changes the entropy, and all those things. So that we're looking at all these different characteristics and the way their interplay. So we have a superheated gas that enters into the compressor. The compressor draws it into the cylinder and compresses it. Now, during that compression, we know obviously the increases in pressure because we're going vertically on the chart, but we also increase in temperature as well. Our suction temperature in this case is about negative 10 degrees Celsius. And by the exit, we're somewhere up here between 50 and 60 degrees Celsius. We'll call it 55. So we've crossed several isothermal lines. We've traveled almost perfectly along the lines of constant entropy, or the isentropic line. That doesn't normally exist in the real world, but that's the way I charted it. My actual superheat value is probably a little bit higher, which would put it a little bit to the right of the line of constant entropy, meaning it's not reversible. And I know it's not reversible because, well, that doesn't really exist. So, discharge of the compressor, we're way up here, we're nice and hot. We're nowhere near the saturated vapor curve. So we're more of a rarefied gas, but we're at a higher pressure, we're at a higher temperature. So it discharges the compressor, and it exits the compressor at more or less a constant pressure at the high side, the head pressure level. Upon leaving the compressor, it immediately starts to cool, and we start to cross back over some of those lines of constant temperature, the isothermal lines, and we're cooling that slightly until we reach the point of the saturated line on the saturated vapor line on the saturation curve here. From then on, if we remove any heat at all, that is, we're reducing in enthalpy, the number of BTU per pound or kilojoules per kilogram, doesn't matter which units you're talking about, as long as you keep them constant, unlike this video. As that higher temperature exists there than the ambient environment, it's discharging heat to the environment, warming the air around the condenser. Discharges all that superheat. We have a saturated vapor again, and as it continues to cool and to warm the environment around it, the enthalpy drops, and we start to get condensation. We get more and more liquid. So as we travel across at a constant pressure and a constant temperature that we're condensing, the quality of the refrigerant changes. That is, for every pound or every kilogram that persists in a purely liquid state. It's not really too important to discuss that, but if you take this line and you divide it by 100 parts, then right here you have 100% quality, and here you have 0% quality. I misspoke there. So the quality is the actual amount of vapor. So purely liquid, saturated, is 0% quality. Purely vapor, saturated, is 100% quality. Again, not too important there, but just to get a general idea of where it exists there on that isobaric line, that is line of constant pressure. Okay. We've discharged a lot of heat to the environment. We've lowered the pound or kilogram of a certain amount of enthalpy, and we've condensed that vapor into a liquid state. Now, if we continue to cool that liquid beyond the saturated liquid curve, we call that subcooling. Because once we get over here, these isothermals are no longer horizontal, they actually start to travel vertically. So as we continue to cool it, we remove enthalpy, we're in a liquid state, we start to reduce in temperature. And the more temperature, the more the heat we discharge, the lower the temperature. And whenever we finally enter the throttling device and exit the throttling device, we have less flash gas. And flash gas is something that you can read about in any good refrigeration textbook. Try to discuss it a little bit here, but let's go with this line right here, and let's assume that we subcooled to that point there. We enter the throttling device. The difference in pressure here kind of dictates the flow through our throttling device. So that pressure component of the enthalpy up here, that is the pressure that was added by the compressor over here, and this pressure difference dictates the flow, and the pressure gets converted into velocity. And because we have that restriction there, that fine point, or that maybe that TXV or capillary tube, whatever it happens to be, we turn that pressure into velocity, and then upon exiting the throttling device, we enter in an area of the evaporator that's at a much lower pressure. And most of that pressure component that turns into velocity ends up finally resulting in flash gas, because all that high-speed liquid refrigerant coming out of the throttling device immediately starts to get very turbulent and all mixed up, and it essentially amounts to kinetic energy, which is similar to a temperature rise. And if we have a temperature rise, we're going to have we're immediately above the saturation line already. We're going to get some flash, and some of that refrigerant is going to boil off to absorb essentially the heat energy from that, or the pressure component of the heat content. Not too important here, but we're also going to have some flash because the refrigerant's still at a higher temperature. So upon exiting the throttling device, it self-refrigerates first. So a certain portion of the refrigerant, say in this case maybe 20% or more of the refrigerant, flashes off and cools the remaining. So if we have 20% flashed off to vapor, the remaining 80% still exists as a liquid that can do cooling work. Now, of course, this evaporator should exist at a lower temperature than the heat load, so that it can absorb heat. And as that liquid evaporates and absorbs heat, it's going to increase in enthalpy. And we're going to travel across the chart again, increasing in enthalpy the whole time, absorbing heat from the environment, lowering the temperature of the environment, until we get back to the saturated vapor line. At which point we cross the saturated vapor line, we're in the suction line, and we're going to end up as a more rarefied gas, increasing temperature and crossing these isothermals again. So why can this be useful? Well, apart from just kind of visualizing it here, we can look at certain characteristics. So for instance, the first thing that we should really look at is the difference in temperature and pressure between the high side and the low side. larger the pressure differential and temperature differential between the high side and low side, generally the lower your overall coefficient of performance is going to be. The more work the compressor is going to have to do. And we can look at that in a couple of different ways. Generally, the COP is dictated or is determined by comparing, in a cooling application, is by comparing the enthalpy change of the refrigerant across the evaporator, the effective cooling that it's doing, to the enthalpy change of compression. Okay. So how do we do that? Well, we look at the actual enthalpy values at different points in the system to kind of get a idea. So at the exit of the throttling device, we can look and we can figure out what the actual enthalpy state, say the kilojoules per kilogram or BTU per pound. We can say, okay, well, it entered at 250 kilojoules per pound and it exited the evaporator at 540 kilojoules per pound. And the difference between those two is the amount of heat absorbed by the refrigerant in the evaporator for every kilojoule or every pound, whatever units we're discussing there. Likewise, we can look at the compressor itself and we can say, okay, well, at the inlet of the compressor, say right there at that point, we can say, all right, it was at 560 kilojoules per kilogram, and at the exit, it was at 630. Okay, we can look at the difference between those two. The difference there, the amount of heat added during compression, is essentially the same thing as the amount of work that was being done. If your electric compressor were 100% efficient, you should actually be able to determine what the mass flow rate is through the system, but your compressor is not 100% efficient. If you know the efficiency of it, I suppose you could use this information, this difference in this change in enthalpy, and compare that to your compressor amp draw or the wattage consumed, to determine how many pounds per minute or per hour or what have you are flowing around. But let's not get into that too deeply right now. So just from kind of a theoretical standpoint, if we divide the change in enthalpy from compression into the change in enthalpy from the evaporation portion of the cycle, we should be able to determine what our actual COP is. So again, whenever we're looking at a larger pressure differential, we can see that if, assuming that the compressor operates on these lines of constant entropy, whenever we have say a higher head pressure, this line, the compression line, is going to come out a little bit further. So the total amount of enthalpy change during compression could be proportionally larger to the amount of cooling work done on your evaporator. So the theoretically possible COP decreases. So what you can actually get out of it is likewise going to probably decrease. The other thing is we can see the shape of the saturated vapor line on the saturated curve leans off to the right. So if our pressure increased slightly, or let's say it's increased significantly, and the discharge temperature and pressure were way up here, and we discharge at a constant pressure, and assuming the condenser and the evaporator and everything, there's no pressure drop, but let's just keep it simple here, and we come across at a constant pressure, we see that the saturated liquid curve is much further over to the right. And in order to get much subcooling at all, because we're assuming our head pressure is so high because the ambient temperature's slightly higher too, if we can't get quite far enough over here to discharge a lot of that enthalpy and lower this refrigerant temperature, we're only going to end up down here, maybe somewhere in the middle, once we finally exit the throttling device. So a lot more of a refrigerant had to flash off to cool the refrigerant that we couldn't cool in the condenser. So there's less liquid being circulated that's actually doing cooling work. So not only did the size of our the quantity of, or the magnitude of the enthalpy change during compression increased, but the magnitude of the enthalpy change for evaporation decreased. So we can see how our overall COP decreased. So we can actually visualize here and see what the change in subcooling and the change in head pressure has an effect on. You can kind of do a really simple theoretical COP calculation if you have an idea what the pressures of your system are going to be, and you're looking to figure out what the maximum possible COP is going to be for a perfect heat pump of that size. By simply dividing, I want to say we divide the absolute evaporator pressure. Now, this is assuming you're doing cooling work. The absolute evaporator pressure, that is not the gauge pressure, but the absolute pressure. Divide that by the difference between your low and your high side pressure. And that should give you the maximum possible COP, Carnot efficiency, the maximum possible COP for that pressure differential. The real world is always going to be less than that theoretical one, but that theoretical value. But anyway, I'm getting off topic here. So something else that can hugely affect the performance of the system here is, let's say we don't have a very well insulated suction line, and after all your refrigerant has been boiled away in the evaporator, really warm suction line on a nice hot day returns to the compressor and increases in temperature, let's say 40 or 50 degrees. And so it crosses several of these isothermal lines on its way to the compressor. So it increases in temperature dramatically. Upon actually entering into the compressor, our superheat, or our superheat horn essentially ends up way out here. So we can see there's a huge amount of enthalpy added unnecessarily. Now, the actual amount of work that was done is still essentially from that point to that point, the enthalpy from there to there. We don't want to include the superheat added after the evaporator. However, we also have to consider that heat needs to be rejected on the condenser side after the discharge of the compressor. So it's essentially taking up some of the capacity of the condenser to discharge heat. You want to use that condenser to actually do some condensing to more effectively discharge heat, because we work a lot better if we work off this latent heat and we don't work in the sensible heat area over here. What else can we talk about? Okay, the throttling device. One of the reasons that I have two vertical lines drawn here is because this one is essentially without a heat interchanger, and this one is. So because I have my capillary tube wrapped around my suction line, I'm able to more effectively subcool that refrigerant before it exits the capillary tube. So that's why I'm way over here in the subcooled region. This one's without the heat interchanger. So we're just we've got a lot more flash, as you can see right there. So with the heat interchanger, I'm able to cool a lot more, a lot less flash gas, and I have more liquid in the evaporator doing cooling work. The expense of that, the cost of that, is that heat has to still go somewhere. We don't just get rid of an enthalpy entirely. We end up discharging into the suction line. So I have more superheat on this side here. So my compression, my superheat horn on this side ends up extending out a bit further. I'm not really sold on the heat interchanger yet entirely, but time will tell. So that's kind of a visualization of that. Something seemed a little askew because it seems like I'm getting a lot more subcooling on this side than I am adding superheat on that side, and this is just based on the temperatures and pressures that I measured around the system. So some of these values might be a little bit askew, because you would assume if I'm discharging X amount of enthalpy on this side, that I would probably be adding that same amount of enthalpy on the other side. So I would expect those two to be more comparable, but anyway, I don't see that. It was kind of lighter, that green one and that yellow horn there, just the same machine running at probably slightly higher ambient conditions, slightly higher evaporator pressure and temperature. I don't remember what the conditions were of this. This was done some weeks ago, but I just pulled it out because I happen to have this diagram already listed up here. So what else can we discuss here? We do actually list the quality down here at the bottom. So it's not really all important. Oh, okay, I know. So like I said, every refrigerant is going to have a horn like this. Water is going to have a horn like this because water is a refrigerant. And ammonia and 22 and R134A and everyone else. What I think is interesting, another interesting aspect of these horns, is they're a little better for refrigerant selection. Okay, why? Well, because if you look at a couple different refrigerants, I'm sure you've noticed by now that they all have different pressure temperature relationships, and they all have different boiling points at atmospheric pressure. Lower, some of them are much higher. Methane is extremely low, like negative 200 and some odd degrees Fahrenheit, very, very cold. Whereas something like isobutane is at like 12 degrees Fahrenheit, and butane itself is like 30 or 31 degrees Fahrenheit. So you have a wide range, and there's even some that have a boiling point at atmospheric pressure well above normal ambient room temperature. So what a chart like this kind of gives you an idea of whenever you're kind of selecting the refrigerant that you want is you can look at the temperatures and the pressure, well, specifically the temperatures, because we're not so concerned about the pressures. The pressures go along with the temperatures, but unless we end up going, super high in pressure or end up operating in a vacuum, we're not going to look at that too much. But we're going to say that, for our particular application, say this is a refrigerator or a freezer. So I'm operating down here in this region. Now, let's say that this was going to be kind of a high temperature a heat pump, and let's say it was going to operate up in the 90s or 100 or 110 degrees Fahrenheit, so really quite warm. We would be operating way up here in the top of this horn. Well, you can see that the width of the horn towards the top is much narrower than the width of the horn towards the bottom here. And as we talked about before, the shape and the lean on this saturation curve changes, and it gets more pronounced towards the top. So if we were to operate this as a high temperature heat pump up here towards the top of the horn, we can see that the enthalpy change that occurs upon going from a vapor to a liquid or a liquid to a vapor, it's much smaller for every cycle of 1 kilogram or one pound of refrigerant. So not only do we have to circulate more refrigerant to effectively do our cooling or our heating work, but also we have to consider the amount of effective subcooling that we can do, because we're going to have to discharge more of that enthalpy, that heat, by lowering the temperature, doing actual sensible cooling of the liquid. Whereas down here we can operate more at a constant pressure and temperature and discharge that heat at a constant temperature and work in the latent heat part of things. So if you compare a couple of these charts, you get a better idea what I'm trying to get at here. And that's one of the reasons why, R22, you wouldn't really see that too much in, say, a refrigerator or a freezer, because it's more of a medium temperature or a high temperature refrigerant. Likewise, R134A, you don't see that used in air conditioners or heat pumps or things like that. And then you can get into things like blends and stuff where they try to kind of change the shape of this curve and develop new refrigerants that I think usually have less of a pronounced lean to the saturation curve. But with those blends, you also have slanted or sloped condensation and evaporation lines, because they're occurring across a range of pressures rather than these more or less horizontal ones here. So I don't really know where else to go with this. I'm happy that I even got through this part of the video, or any part of this at all. If anybody has any questions, by all means, send me a message or comment or email or whatever. I'd love to talk about these some more. Maybe in the future I can do more examples with the actual system that I'm working with. There's a lot more little nuances and interesting little things to to understand with a pressure enthalpy curve like this. There's also little, if you kind of zoom into some of these little parts, like for instance the suction valve or the discharge valve in the valve plate of the compressor, these lines don't just go over and up, they actually go over and across and down and back and up, and there's all kinds of weird little things because you have throttling that occurs where there's tiny little minute pressure changes in the reed valves of the valve plate. Crazy little stuff, stuff that, you know, a person like me or you probably isn't going to be getting into. There's also things like the slant of the throttling line over here. We kind of assume that it's vertical, but in truth, this is not a reversible process. It's not isentropic, and it's usually not isenthalpic either. So it's not usually completely straight. So there's all kinds of fun stuff with these things, and I don't know why I get so excited about them, but I really do. So I'm going to review this video a little bit and see if it's worth posting, and probably post it anyway. So thanks for watching.